Let's talk about expected value. You should have read through the supplemental reading available on the course webpage and in class completed the expected value worksheet. This video will walk you through a few more examples of expected value and standard deviation, as well as how to interpret these values. Expected value means to find the long-run average of a random variable. In other words, if a random process were repeated many times and a number assigned to each outcome, what would the average of those numbers be? Let's use the random process of having a family as an example. We can look at a population of students and for each student, assign a number, that is the number of siblings the student has. The table shown does just that. It was found that 14 of 173 students in our population were only children or had 0 siblings. Therefore, the probability or long-run proportion of the long-run proportion of students with 0 siblings is 14 out of 173 or 0.08. Similarly, 68 students of 173 from our population had 1 sibling, so the probability of having 1 sibling in our population of students is 68 out of 173 or 0.39. We can find the remaining probabilities the same way. The random variable we are analyzing is number of siblings, and we may want to know about its center and its spread. Expected value, or the long-run mean, is one way to measure center. We denote expected value with E of x, where x is the random variable number of siblings. To calculate expected value, multiply the value of the variable number of siblings by the probability of that value happening, and sum those for all possible values. Here you see the value of the variable number of siblings in the first column. So students can either have 0 siblings, 1 sibling, 2 siblings, etc. The second column contains the probabilities we calculated on the previous slide. 8% of the population were only children. 39% of the population had 1 sibling, etc. In the third column, we're going to write the product of these first two values. 0 times 0.08 gives us 0.00. 1 times 0.39 gives us 0.39. 2 times 0.31 gives us 0.62, etc. Finally, to find expected value, we will sum these numbers in the third column. 0.00 plus 0.39 plus 0.62, all the way down to our final value, 0.12. That gives us a mean number of siblings in the population of 1.84. Now, let's think. Does that number make sense? A single student cannot have 1.84 siblings. But remember, the expected value is the long-run average. So in the population, the average number of siblings is 1.84. This tells us something about the population, not about an individual student. Well, why can't we just add each number of siblings and divide by the total, like we usually do to find an average? So that would be like adding 0, 1, 2, 3, all the way down to 6 and dividing by 7. Why doesn't that work? Well, the typical way to find an average assumes each of these values is equally likely. We know that's not the case because we see the probabilities of each value here in the second column. We have to take into account those probabilities when we find the expected value. Since our probability distribution was created from a finite population, meaning there are only 173 students, not an infinite number of students, the mean number of siblings can also be calculated by adding the number of siblings for each of our students. So 14 students had 0 siblings, I could add 0 14 times. 68 students had 1 sibling, I could add 1 68 times. 53 students had 2 siblings, I could add 2 53 times. And keep going until I get to all 173 students in my population. I could simplify that math just a little bit here in this second equation by taking the number of students times their number of siblings and adding that up for each of my number of siblings. And I get the same answer of 1.84. This will only work for finite populations, where I can actually count how many people are in the population. Also note that this probability distribution only goes up to 6 siblings, which may not be realistic in the real world. Recall again that the expected value is the mean value, or where the graph of the distribution balances. Here we see a histogram of the distribution of number of siblings, and our balancing point, or our expected value, is 1.84, telling us that the expected value is in fact a measure of center for a random variable. But we are not only interested in center, we also want to know about variability. Thankfully, or not, we can calculate the standard deviation of discrete random variables. Start with the same first two columns as before. We want to look at x, the values of the random variable, and p, the probability of taking on those values. Then what we'll find is the squared deviation. In other words, we'll take 0, the value of x, minus the mean, or expected value that we calculated, 1.84, square that number, and that's where we got 3.3856. 1 minus 1.84 squared gives us 0.7056. Again, repeat that process for all the other values of x. We're almost there. Now multiply the probability in the second column times the squared deviation in the third. 0.08 times 3.3856 gives us 0.2708. 0.39 times 0.7056 gives 0.2752. Now let's add up everything in this fourth column. If I add up the squared deviations times the probabilities for all the values x can take on, I get 1.5944. Then the standard deviation of number of siblings will be found by taking the square root of that number, and the square root of 1.5944 is 1.263. Now, as you might have found, we care much more in this class about interpreting values than we do about finding them. So first, how would we interpret the value 1.84? Well, we actually already did that on the previous slide. It is the long-run mean number of siblings in this population of students. How about interpreting the value 1.263? Again, standard deviation is the average distance each observational unit's value is from the mean of the data. That tells us each student's number of siblings is, on average, 1.263 siblings above or below the mean of 1.84. On the next slide, you'll try another example. I would recommend putting the given information into a table which includes the value of the variable and the probability, just like we did here in our first two columns. Note, make sure that you include all possible values the variable could be so that the probabilities column will sum to 1, just like you saw here. Pause the video here to complete this problem, then play to check your answer. Okay, we want to know, is the warranty a good deal? Let x be our random variable representing the cost to repair the item without a warranty. So we need to assume we did not buy the warranty. If that's the case, there's a 1 in 50 chance you'll need a repair, and it will cost you $200. There's a 49 in 50 chance you will not need a repair, and it will cost you $0. Let's go ahead and use this table to find the expected value. You should have gotten an expected value of 4. What does this mean? The long-run average cost of repair without a warranty is $4. Note that if you bought the warranty, your cost is $10, regardless of whether you needed a repair or not. Let's try calculating standard deviation as well. Recall the expected value of x is 4. So to find standard deviation, we take a value of x, 200, minus the expected value, 4, square that deviation, and multiply by the probability x equals 200, which is 1 over 50 for this case. Repeat that for all other values of x. To find the standard deviation, we then sum those products, take the square root, and get a value of 28. Make sure to check my math. What does this number mean? Without the warranty, over the long run, the repair cost is roughly $28 away from the mean repair cost of $4 on average. Some final notes about expected value. The expected value is the average or mean value of a random variable over the long run or over many, many trials. It may or may not be an actual possible value of the random variable. In fact, usually it isn't, like 1.84 siblings. In gambling, lotteries, insurance, extended warranty, etc., you can be pretty sure that your expected cost per event, if you play or buy, is more than if you don't. The house usually wins. However, for insurance, for example, you might prefer the peace of mind of knowing your fixed costs. Or for the lottery, you might want the thrill of the possibility of winning, even though you lose on average. And of course, some final notes about standard deviation. As always, standard deviation is approximately the average distance we would expect to be from the mean over many, many trials. In general, it's useful for comparing two random variables to see which is more spread out. As an example, let's say two cities both have an average yearly temperature of 65 degrees, but one has a standard deviation of 5 degrees, and the other has a standard deviation of 20. Where would you want to live? Or investment funds. Let's say one investment fund has an average rate of return over many years of 8% with a standard deviation of 2%. The other has an average return of 10% but a standard deviation of 20%. The second one is higher on average but is much more volatile. Which investment fund do you prefer?